Okay, welcome back to class DIT 2314 data structure with topic number 3 stack and queues. Okay, so today we will going to explore the two of the most fundamental data structure in computer science, which is the stacks and queues. So let us begin with the first part, which is the introduction to stack. Okay, so stack is a linear data structure that follow a very strict specific order for performing operation. It operates on the LIFO principle. LIFO, which stands for last in, first out. So this means that the last element that you add to the stack is always the very first one to be removed. So this is the important rule of a stack, is the single end access. So all insertion and deletion will take place strict at one end, which we call the top of the stack. And the great everyday analog of this physical stack is the cafeteria plates. You can only add a new plate to the very top, and you can only remove the plate from the very bottom. Okay, a stack abstract data type ADT operation. Now the abstract data type that we have understand what a stack look like in conceptually. So let's interact with the abstract data type or the ADT operation. So we have four main operation and a couple of utility checks. Number one, the push operation. So this is a new element to the top of the stack that increasing its overall size by 1. Next, we have the pop operation. This remove and returns the top element from the stack that increase the size by 1. And we have the pick or the top operation that allow us to inspect and return the value of the top element without removing it from the stack. And then we have the isEmpty, isFull check. So this is a boolean utility that operates that check whether the stack is completely empty or has reached its maximum capacity. Okay, next we have the array-based implementation of stack. So how do we actually build a stack in code? So the underlying storage use understand one-dimensional fixed size array to keep track of where the loop of our stack is, and we maintain an integer variables commonly named top, which is initialized to 1 to -1 when the stack is empty. So because of our array has a fixed size, we have to watch out for two critical conditions, which is the overflow condition. So this occur when you attempt to push an element into a stack whose top index has already reached the maximum array boundary. And then you have the underflow condition. So this occur when you attempt to pop or pick from a stack where the top index is still at -1, meaning there is nothing in the stack. So while the array are simple, the fixed size can be restrictive. So this brings us to part 4 with the linked list based implementation of stack. So instead of fixed array, we use a dynamic structure that made of a dynamically allocated linked list of nodes. So So we treat the head pointer of the linked list as the top of the stack. Inserting a new node at the head takes constant time, or the 0-1 time complexity. Most importantly, this gives us a memory flexibility, completely eliminating stack overflow risk caused by fixed capacity limit. You stack in now bounded only by the available system RAM. Application of stack. So stack are not just theoretical exercise, they power the software we are used every day. So let us look at this part 5, the application of stack for function call management. So computer system use a call stack to manage active subroutines, functions and method invocation in programming. So every time a function is called, its execution context which store local variables, parameter values and a return address. So it's pushed into the stack. So when that function finishes executing, the system pops its stack's set frame to resume the calling function. And furthermore, recursion relies entirely on the stack call stack to track nested function calls and unwind them correctly. Moving forward to part 6, the stack play a critical role in expression evaluation. So computer use the stack to evaluate mathematical expression written in various notation, such as infix, prefix and postfix. Stack handle the mathematical operation predecessors and parenthesis grouping effectively during computation. For example, during postfix evaluation, the algorithm iterates through an expression, pushing operands and hoping them to apply operator when they appear. The stack also helps in error detection, allowing compilers to spot mismatched parentheses, brackets, and syntax error within complex mathematical statements. How do computers convert standard mathematics into a form that they can easily evaluate? So let us examine in part 7 the infix to postfix conversion using stack. So the infix definition, so this is a standard human readable mathematical notation where operators sit comfortably between operands such as a plus b. And then we have the postfix definition. This is the computer-friendly notation where operators follow the operands, completely eliminating the need of parentheses such as AB plus. So the conversion algorithm uses a stack to temporarily hold operator based on predecessor rule, which scan infix expressions. It generates output by appending operands directly to the output stream while shifting operators through the stack. Let us wrap up our discussion on stack with the part 8, the backtracking algorithm and browser history. The stack provide essential backtracking support by storing previous decision state in algorithm like maze solving, puzzles and game trees. In everyday application, text editor and graphic design software use two separate stacks to manage undo and redo operation. Similar, web browser use back and forward stack to track visited web pages and enable navigating history. So this is the ability to achieve a state restoration allows programs to easily revert to prior operational states when a path fails or it is cancelled. Introduction to queues. So now let's us transition smoothly from stacks to our second major data structure in part 9, which is the queues. While a stack is LIFO, last in first out, a queue is a linear data structure that maintains a sequential order based on the FIFO principle, the first in, first out. So this means that very first element added to the queue is the first one removed. So unlike stack, which only have one end, queues have dual end access. Operators occur at two distinct ends. Insertion happen at the rear and deletion happen in front. The classic analogy of this physical line of people waiting for service. People enter at the back and leave from the front. In part 10, let us look at the standard operation of a queue abstract data types, ADT. Queue operation adds a new element to the rear or tail of the queue. Dequeue operation that remove and return the element located at the front of the queue. Front or pick operation that inspect the element at the front of the queue without removing it. Utility checks include the operation to verify if the queue is empty or full is full. Implementing the queue using a simple array brings some interesting challenges. So as we see in part 11, a linear array-based queue uses two integer pointers, front and rear, both initialized to -1 to track queue boundaries. During operation, enqueuing increments rear and dequeuing increment front as items are processed. However, this creates a major issue: wasted space. As items are dequeued from the front, those vacant spaces cannot be easily reused. This leads to a false overflow condition, where a linear array queue reports that it's completely full even though the empty space remains at the very beginning of the array. To fix the wasted space problem of linear queues, we introduce circular queues in part 12. So the circular queue use a ring buffer concept that connect the end of the array back to the beginning to form a continuous circular loop. It uses modular arithmetic calculation, specifically rear plus 1 capacity to wrap pointer indicates around the array. This successfully achieves space reutilization, allowing us to reuse vacant slots left behind by the queue element. Just like stack, the queue can also be implemented using linked list, which we cover in this part 13. By using the dynamic nodes, we can completely avoid fixed size constraint. So instead of one pointer, we maintain two explicit pointer reference, a head pointer for the front and a tail pointer to the rear. Both enqueuing at the tail and dequeuing at the head execute in constant 0-1 time complexity. allowing the memory to adapt dynamically to real-time application demand. Next, let's us look at the specialized variant in part 14, the priority queues. A priority queue is a specialized queue where every element is associated with a specific priority value. The ordering rule here is simple. Elements with higher priority are queued before elements with lower priority regardless of the arrival order. If elements share the exact same priority, they fall back to standard FIFO ordering rules. So these are commonly implemented using binary heaps, balanced search trees, or unordered array. Priority queues are important in high performance computing, as we will explore in part 15. Operating systems, so they manage the CPU process scheduling, giving high priority to critical system tasks over background jobs. Network routing, so they prioritize data packets in routers to ensure low latency for time sensitive traffic. Graph algorithm, so they power core greedy algorithm like the Dijkstra's shortest path and Prim's minimum spanning tree algorithm. Event driven simulation, they manage to chronological event execution queues in simulation and discrete event modeling. Moving on to part 16, let us look at the double-ended queues or the dequeues. So a dequeues is a generalized linear queue that allow insertion and deletion operation at both end, front and rear. It acts as a hybrid flexibility structure combining the operational capabilities of both stack and queues. There are also restricted variants such as input restricted and output restricted dequeues. Common use of this case include the job scheduling algorithm, palindrome checking, and sliding window maximum calculation. How do stack and queues stack up against each other performance-wise? Let's just review in part 17. Number 1, by time complexity. Basic operation like push, pop, and queue and dequeue all run in constant 0-1 time across efficient implementation. Space complexity. Both structures consume linear 0n space complexity relative to the number of store element. Access limitation. Neither structure allow random access. Element must be accessed in strict accordance with the structural rules. Let us look at some more real-world application of queues in part 18. Print spooling. So manage the document print job sent to a shared power office printer in the exact order they arrive. Customer support system, handling incoming customer service call queues or help desk ticket routing. Asynchronous data transfer, that buffer data stream between hardware devices running at different speed, such as keyboard input buffer. Web server request handling, that queues incoming in HTTP requests in web server before dispatching them into worker threads. Before we conclude, let us talk about the common mistake to avoid. In part 19, the common pitfall and error handling. Stack overflow, underflow. Failing to check bounds causing the program to crash when pushing to full stack or popping empty ones. Queue pointer drift. Incorrectly updating front and rear pointers lead to lost data or permanent queue lockup. Memory leaks. Forgetting to free deleted nodes in linked list implementation cause gradual memory exhaustion. Concurrency conflicts. Multi-threaded access to shared stack or queues requires proper synchronization lock to prevent rest condition. Finally, let's wrap up this part 20 with summary and transition. So our core takeaway today is that the stack and the queue enforce a disciplined access pattern with LIFO and FIFO that are important for system and application logic. They serve as an agricultural bridge between simple linear array and advanced dynamic pointer based structure, forming the backbone of parsing engines, search algorithm and operating system schedule. So this is the end of this topic number 4. We will continue with topic number 5. Thank you.